In this lecture, we will be studying Newton's method for nonlinear optimization. First, let's remind ourselves of how Newton's method works for a function of a single variable. So solving equations is often difficult or even impossible to do analytically. We have a theorem from Abel in the early 1800s that says there's no formula giving the solution of an arbitrary polynomial equation of degree 5 or higher in terms of algebraic combinations of its coefficients. In this case, think of something like the quadratic formula. For a general quadratic polynomial, we have a formula that finds a solution of that quadratic set equal to 0. But once we get to higher degree equations, or to just equations in general beyond polynomials, we don't necessarily have that method for finding an analytic solution. One class of methods to numerically approximate solutions to this type of problem are called iterative methods. And the idea here is we have a function and we want to find a root of this function. So we want to solve f of x equals 0, and we want to generate a sequence of guesses that converge to the solution that we seek, r. So in here, by r, we mean that r is the root of f, a root of f. And we define what we mean by convergence. A sequence of approximations converges to the number r, provided that we can make the nth entry in this sequence as close to r as we desire simply by choosing n sufficiently large, so by going far enough down the list. Mathematically, this means for any epsilon greater than 0, there exists an n in the counting number, so think of an n as an index in this sequence, such that the difference, the magnitude of the difference between that nth term in the sequence and that solution r is smaller than epsilon once you're past that capital N in the list. Newton's method is such an iterative method. And so in Newton's method, our goal is to approximate this root of the function f of x. Newton's method uses a tangent line approach. So Newton's method is for functions where we actually can calculate a derivative. So let's think about the tangent line at this point, x naught, f of x naught. So let's form the tangent line. If we draw it, we will get something like this. So this is our tangent line at the point x naught, f of x naught. We know that the slope of that tangent line is f prime of x naught. To write down the equation of that tangent line, we use our point slope formula. Now we know that y naught is f of x naught, but the slope will be f prime of x naught. So putting that all together, we have y minus f of x naught equals f prime of x naught times x minus x naught. What Newton's method does is, starting with this x naught as our initial guess for this root, we form this tangent line, and our next guess, defined as x1, will be the root of that tangent line. So how do we find the root of that tangent line, given that we have the equation for the tangent line here? Well, we note that at that root, the y value for that tangent line is 0. So we plug in 0, and we seek the x-coordinate associated with this y equals 0 value. What we have here is going to be one form of how we write down Newton's method, and the other we solve for that x. So notice, solving for that x, we can divide both sides by f prime of x naught, as long as f prime of x naught is non-zero. And so we get negative f of x naught divided by f prime of x naught is equal to x minus x naught. Solving for x, we have x equals negative f of x naught over f prime of x naught plus x naught. And this x is what we just found here, and we're calling x1. And we're using a superscript because we are working in the next slide with functions of several variables, and we use the subscript to denote which entry of our vector x that we are speaking of. So the superscript in parentheses tells us which iteration we are on. Note that we have this written here. So this is now for the n plus first x, given the previous guess xn. So this is what we define to be the Newton method sequence. And the idea here is you can iterate this. So what we would do for the next guess is we would use this x1. Go up here, find the tangent line, and then find its x-intercept. And you can see graphically that we would be honing in on this root r. A couple of subtleties. It's important to recognize that there are situations where Newton method does not converge. And if it does converge, it will converge to a solution of f of x equals 0. But it also depends heavily on the initial guess. So with this depiction here, we have our horizontal axis here, and we can see that if you start with an initial guess here, we expect to hone in on this root. But if we were to start with an initial guess over here, we should expect to hone in on this root here. So our initial guess does play a role. So oftentimes with Newton's method, your initial guess is something that you use information about the function that you already have to make some type of an intelligent initial guess. So it's critical to recognize that for any iterative method, you have to start somewhere. So you have to have some initial guess. Now we want to use Newton's method for functions of n variables, and we're really setting up for optimization. So first we want to talk about a slightly different setting that we're used to. We're going to talk about a function g from Rn to Rn, and it's important to recognize the range here is Rn, so this is a vector-valued function g. It takes in a vector as input and gives a vector as output. And we're setting up to solve the system g of x equals the 0 vector. It's a little more natural to look at it this way. G of x here gives you an n vector, g1 of x, g2 of x, gn of x, where each one of those individual g sub i's, these go from Rn to R1. So each entry here, when you give it an x, is a scalar. And our goal is to solve this system of equations, starting with some initial guess x naught. So that's a vector as an initial guess. And what we do is extend the Newton method that we just looked at to a vector version. So this was one way that we could write down Newton's method for a function of a single variable. And now we write that in this vector form. So instead of f of xn, we'll have g1 of xk. Then here we have the gradient of g1 of xk, dot product xk plus 1 minus xk. That's the analog of this, equal to 0. And we have this equation for each of these equations coming from g. So we have an equation like this for g1. We have an equation like this for g2, up to an equation like this for gn. And the idea there is that instead of taking a tangent line and finding its root, we are looking at the tangent hyperplanes for each one of these components of G. We know when we're working in higher dimensions like this that this here, G1 of xk, is a scalar. The gradient of G1 evaluated at xk, remember we know xk, so this is just a vector of numbers. Xk is a vector of numbers, that's our previous guess. Xk plus 1 is the unknown. So this is a scalar plus some linear combination of the entries of xk plus 1 equals 0. This is a hyperplane in Rn plus 1 dimensional space. The key is that we are solving n of these simultaneously. To see what this is graphically, consider the case where n equals 2. Our hyperplanes, in this case, are just planes. So this would be, say, the first such plane. Well, the first such plane being equal to 0 will give you this entire line in the x1, x2 plane. Well, what about the second plane? Maybe it looks something like this. That plane being equal to 0 gives us this entire line in the x1, x2 plane. But the key is that we are solving them simultaneously. As long as these planes are not parallel, these planes in the x1, x2 plane intersect in a point. And this is the point we seek. This is what we mean by solving these simultaneously. So for some notation, let's let this be a matrix. So notice G and the gradient are both bold. The idea being that's different how we usually write traditional gradient as a vector. This is just special notation for the Jacobian matrix of G of x. And so the Jacobian matrix of G of x just means that entry ij of this Jacobian is the partial derivative of gi with respect to xj. So it's a matrix of all of these first order derivatives for our vector valued function g. If we put all of that together, that system of equations can be written as that Jacobian matrix times xk plus 1 minus xk equals negative g of xk. This collapses all n of those equations into one matrix vector multiplication equation. If we can invert this Jacobian matrix, we can multiply both sides of this equation by that inverse and solve for xk plus 1. If this is not invertible, we say that the sequence is undefined. And so the idea here is you can't have two parallel hyperplanes that come out of that system. That way you get one point where all of these equations are satisfied. And notice we do write both versions, because when you get into high dimensions, oftentimes you're not just calculating the inverse of the Jacobian matrix like this. You need to do some things in linear algebra that are a little more clever depending on the structure of the Jacobian. This defines our Newton method sequence when we are working in n-dimensional space like this for a vector valued function g. So it's important to recognize, again, g has a domain of Rn and a range of Rn. Well, the natural question to ask now is, how does this relate to optimization? We're minimizing a function f of x. Our objective function is going from Rn to R. So why are we looking at this case where the range is Rn? And the reason comes down to our first order necessary conditions for our minimization problem. And recall, if f of x is twice differentiable, our first order necessary conditions for a local minimizer is that the gradient of f is equal to the 0 vector. And what we will do is set the gradient of f to be equal to g of x in the previous theorem. So think about what the gradient of f of x is. The gradient of f of x takes in an x, which is in Rn, and then gives us a vector in Rn. The gradient is a vector in Rn. So we simply go back here and our g will be replaced with the gradient of f. And we seek a solution to the gradient of f equals the 0 vector. We see here, when we make that change, the gradient of f plays the role of g, but that means if we take another derivative here, the Jacobian of g will be the Hessian of f. So we go back into that Newton method equation, and we replace our g's with the gradient of f, and we replace our Jacobian with the Hessian of f. And we now have our Newton method sequence for minimizing our function f of x. And so now we have our theorem here for that type of minimization, and it simply is what we just wrote with g replaced by gradient of f and the Jacobian of g replaced by the Hessian of f. This defines our Newton method for nonlinear optimization. And just like before, it may not converge, it's sensitive to your choice of initial guess, and it's meant to hone in on points that satisfy the first order necessary condition of the gradient of f of x being equal to the 0 vector. And remember that that will pick up on local minima, local maxima, and saddle points. But nonetheless, this gives us a way to numerically approximate points x that satisfy those first order necessary conditions for a minimizer. If you have a nice situation where you know your f is convex, remember those first order necessary conditions become sufficient as well. And so for a convex problem, Newton's method is only going to hone in on minimizers, global minimizers, if it's converging. It's important to recognize that this is a really important line search method for optimization. Many optimization routines will use this as a subroutine. So understanding how Newton's method works really is critical to understand how we find minimizers of optimization problems. And remember, when you're working with high dimensional problems, we are typically not doing some type of analytic solution. We're understanding the properties of our objective function and then using iterative methods to try to find a solution numerically. And this is the classic such method. So we will see this in action in an example in a subsequent lecture. But again, it's important to recognize that Newton's method is one of the most important methods in nonlinear optimization.